All right. Like so much funsies. All right, this is section 4.3, our lecture on subspaces. Before we get into the nitty gritty, I want to talk about some ideas that the book does not connect very well. We have been solving problems that look like one of the following. Uh, AX equals 0 homogeneous equations versus AX equals B non-homogeneous equations. And I just want to talk about the geometry of those systems really quick. We saw that in both cases, um, the options are no solution, one solution, or infinitely many solutions. And one of those cases for the homogeneous system is not a possibility. So in the homogeneous system, there's never no solution. It's only one solution or infinitely many solutions. And then that one unique solution in the homogeneous situation, we had talked about if we just say maybe draw this as a three-dimensional representation here. Let's see. If we had a system in the variables x, y, and z traditionally for some kind of basic algebra class, if you had one unique solution, that one unique solution would only be the origin. That would be the only possibility. But as you then move on to this other possibility, infinitely many solutions, right? Then the geometry starts to get more interesting. So we already know that 0 is going to be a solution no matter what for the homogeneous system. However, as we go up in dimension, one possibility, this is going to be a little bit weird to draw here, but one possibility would be a solution set that's a line. And that line would have to go through the origin. So this would be infinitely many solutions in one dimension or one parameter. But if we have two free variables, as we saw in some of our other examples, then what you're talking about is something like, and this is again going to be kind of messy for me to draw, something like a plane in 3 space that also goes through the origin, contains that origin point. So in the homogeneous system that I'm talking about here, as we go up in dimension in terms of the number of solutions that we have, we never exclude the 0 solution. Oh, this is messy little coloring. But we have either a single point at the origin, a line through the origin, a plane through the origin, or then in some really extreme cases where your coefficient matrix is, say, the 0 vector itself. This is going to be very strange to draw. What you get is an entire three-dimensional solution space. That is all of R3. I'm going to actually erase that. That's a little bit crowded. And then what you're going to see then is as you move over to, in yellow here, the non-homogeneous system for B non-zero, what we're supposed to learn, and the book, again, doesn't do a good job of this, is describe how the solutions here to the homogeneous system, oops, come on, the homogeneous system are related to the solutions to the non-homogeneous system. And the difference is, oh, I'm going to be able to grab this? Let's see how clever I can be. Is actually a simple shift off origin by that column vector that is the B vector. And so before we go on, there's some things that I want to talk about that aren't addressed in this section and haven't been addressed well. That is to say, solving AX equals B is related to solving AX equals 0, which has a solution set X, let's say X, I'll call it X sub C. Later on in this class, when we look at differential equations, we're going to talk about the complementary solution, the solution to the homogeneous system. Maybe that's what I'll do. Let's do that. Let's call this X sub H, the homogeneous solution set. It's related to it, where our then for AX equals B, which can be thought of, it's a terrible arrow, can be thought of as AX equals 0 plus B. What we're going to have here is a shift, so to speak. And so our solution set X is going to be the homogeneous solution set plus a very particular shift related to the B column. Now, as we've been talking about previously, there's a subtle difference, the obvious difference between this solution set that shifted off the origin versus this solution set, and namely that's the origin. We saw that when we talked about vector spaces the other day, in order to be a vector space, we have to have the 0 vector included in our vector space. Otherwise, things like closure under addition and scalar multiplication and inverses and all kinds of algebra properties that we need for solving systems fails. And so what I want to talk about is this situation and how we're inside in this diagram a three-dimensional vector space. Here we're working inside what we call R3. This is our capital V vector space related to our lecture the other day. And what we have here is either the trivial subspace solution set. So in this section, we're going to talk about subspaces, but you can think of them geometrically as solution sets to this homogeneous equation. And in R3, when A is a 3 by 3 matrix and you're solving this, the solution set never has no solution. It'll either have one solution, which will be just the 0 vector, which is the smallest subspace possible, or immediately we go from one solution to infinitely many. And then what you have is either a line through the origin, that's subspace, non-trivial subspace possibility number 1, or you have an entire plane, which is non-trivial subspace option number 2, and then finally the entire vector space itself. So when we talk about these subspaces today, geometrically speaking, while we go through these definitions in a minute, what we're really referring to in this simple situation is, are we talking about the origin, a line through the origin, a plane that contains the origin, or the entire space itself? And then as the dimension of the vector space goes up, the number of possibilities for the subspaces, or how infinite your solution set is going to increase in the number of possibilities. So what we're about to talk about is pretty abstract, but if you can latch on to this visual representation of possible solution sets in terms of their dimension, then that's what we're talking about when we talk about these things called subspaces. So let's get into the formal definition. So before we do, solution sets to homogeneous, oops, can't spell, genius, come on with the lag here, genius, linear systems are subspaces. So we should talk about dimension for a second. M by n is the typical dimension on a matrix. We're multiplying that via vector x, which has to be n by 1. And here we're talking about the result being the 0 vector, whose dimension is m by 1. And so what we're talking about here is an input from Rn. Maybe it's R3, maybe it's R2, maybe it's R12, I don't know. And then an output from Rm, that is to say, the number of components in each one of these column vectors. And so I'm thinking of A as being like a function of X, where A takes vectors from n dimensions and turns it into, turns it into vectors in m dimensions. And while that's very abstract, you as the engineer are typically going to work with a 2 by 2, in which case x is 2 by 1, and then the 0 vector is also 2 by 1. Or typically a 3 by 3, which is times a 3 by 1 vector, turning it into a 3 by 1 0 vector. And so for 2 by 2 matrices, we're working in 2 dimensions. And for 3 by 3 matrices, we're working in 3 dimensions. So if all of this is terribly abstract with the notation, just note that when you have a 2 by 2 matrix, you're working in 2 dimensions. And when you have a 3 by 3 matrix, you're working in 3 dimensions. And so if we were to look at these situations, if this is R2, whatever A is doing, it is either, in terms of the solution set, a single point at the origin, a line through the origin as our solution set, or it would be the entire R2 plane itself. And then as you go up in dimension, you have these possibilities. And again, I drew this up above, but here we have a 3 by 3 matrix. So we have X, Y, Z. And then our possibilities are the origin, a line through the origin, a plane through the origin, or, sorry, these drawings are kind of lacking, the entire vector space itself. And so these are the subspaces possible. So possible subspaces. Here, one of the, let's call it S, not V. Here, the vector space we're working in is R2, and the possible subspaces S are the set that just contains the origin, or the 0 vector. S is, like say, let's see, T times an x1, x2, which is a line through the origin, or S is some kind of T, x1, x2, plus S, x1, x2, which is a plane, as proper subspaces. And then here, the vector space R3, and your possible subspaces are the 0 vector, a line, a plane, and the entire 3 space. And I won't bore you with the notation there, but those are the options. Now, this section begins with a definition. So now that we're kind of up to speed here, definition. Come on. Let capital S be a non-empty subset of an existing vector space called capital V. Oops, my V's are looking terrible, dude. V. Now, the other day in lecture, I put a bunch of vector spaces on the board. And we'll go over those again today, but there were like 4 or 5 of them that you were expected to know. If the set S is a vector space under the same operations as capital V, then we say S is a subspace of capital V. So what are we talking about here? Operations. The other day we talked about the main operations in the vector space being vector addition and scalar multiplication. I'm going to run out of room there. Scalar multiplication. And while those can be defined abstractly, however they're defined in the subspace, they're defined the same way in the vector space. And then we want to note, and this is important for our proofs later, any subspace S of a vector space V is a vector space in its own right. So what do I mean by that? Well, forgive me while I scroll up here. I know some of you are frantically trying to write that down. If we look back at this situation, R2, right, the XY plane, that's a vector space. But there are several things like R2 contained in R3. That is to say, it could be the XY plane itself, but any plane through the origin here is going to be another subspace. And so even though the parent space, the grand subspace here, is this 3-dimensional block, sitting inside it is this 2-dimensional subspace, but 2-dimensional subspaces are subspaces in their own right, right? And so what we have is Russian nesting dolls and turtles all the way down. And even though this is R3, a 3-dimensional vector space, I shouldn't draw this, but I'm going to. That is contained in something that I can't draw. That is a subspace of a 4-dimensional vector space that it's nested inside of. And so it just keeps going up in dimension. We call these all vector spaces, but sometimes you're working in the subspace of a larger vector space, and so on and so forth. And so you have to realize that these are just these nested ideas, this nested hierarchy of dimension and vector space. So, coming back down here, that's what this statement says. If you have a subspace of an existing vector space V, then it's a vector space in its own right. Dad, I know what I want to be when I grow up. This is who I am now. All right. So the other day we talked about a vector space, and I showed you like 10 different criteria, or I guess I didn't do all of that for you guys. I showed you 10 different criteria on what was necessary to be a vector space, and I made a big deal out of 2 of those rules. And the reason I made a big deal out of 2 of those rules is because what I'm about to show you is a shortcut for showing things are a vector space. Instead of doing a 10-point proof to show something is a vector space, we are going to use what are called subspace proofs, which are much shorter and much faster. So let's begin to talk about that. This is one of the big theorems in this section. Theorem. Let S be a non-empty subset of an existing vector space V. So aside here, let's see. The other day I had a laundry list of possibilities, right? I said Rn is a vector space. Complex vectors is a vector space. Matrices with real entries, where the dimension is m by n, is a common vector space we're going to work with. Polynomials of degree n or less with real coefficients is going to be a common vector space. And then later in this class, continuous functions with at least k derivatives over some interval I is going to be a vector space. And so in this section, we're always going to be working probably with one of these vector spaces, and I'm going to call it the parent space. So when we talk about a parent space, I'm talking about the larger vector space in which the subspace is nested. And so back up here in this situation, here R4 might be the parent space of R3, or R4 is the parent space of R3, R2, R1, and then the origin itself. And so we have this hierarchy, and I'm just calling the grander vector space the parent space when we refer to it. There's a reason why I call it parent space, because there's this inheritance that we're going to talk about. I know we're all waiting for our parents to die, and some of them just won't do it. And we want to get their house, and we want to have all their things, and we want to incur their debt, and we'll get to inherit all of that. And the same thing is true here. So let S be a non-empty subset of an existing vector space V. Then S is a subspace of V if and only if the following criteria are satisfied, and these are straightforward. 1, S is closed under vector addition, and 2, S is closed under scalar multiplication, which were the main two properties of the vector space. Now I say two things, but there's really three here. I'm going to call 3 the non-empty portion, and actually there's really 4 parts to this proof. You have to also declare your parent space. And so when we go through these subspace proofs to establish something as a subspace, we want to say, look, I have a non-empty set. I'm working within the existing framework of some known vector space, parent space, and then we'll go through some basic proofs of closure. Okay. So let's see here. Example 1. Show the set of all 2 by 2 symmetric matrices with real entries is a vector space. So when you see a problem like this on the exam or in the book, this is going to be the extent of the directions. It's just going to be the statement. And you're expected to be able to unpack all of that, right? Show the set of all 2 by 2 symmetric matrices with real entries as a vector space. Well, I just briefly here, and I don't have time to write all this down, to show something as a vector space is actually a section 4.2 problem. And that requires you to go through 10 different, a 10-point PowerPoint presentation on all of the different properties. However, if we do a subspace proof instead, we minimize the amount of effort that's required. So before we get into the nitty-gritty, there's some basics that you as the student should be aware of to help you along your journey through this proof. And so the first thing I would suggest, writing your set in set builder notation. Now, if you can do this, then you probably have something actionable to work with. What do I mean by that? Here we're talking about S, which is the set of 2 by 2 symmetric matrices with real coefficients. I could write as A, B, C, D. That's the format. That's a 2 by 2 matrix such that A, B, C, and D are real numbers. Those are the real coefficients. And B equals C. That's what it would mean to be symmetric. Because in order to be symmetric, I need that position and that position to be equal to one another by definition of a symmetric matrix from way back in chapter 2. So another way to write this might be something like A, B, B, C, where A, B, and C are real numbers. So we have format and restriction. This is the restriction. This is the format, or in this case, format and restriction. So now I have something to work with. Now, as we begin here, the first thing, now, declare the parent vector space. This is probably one of the more important steps for you to get out of the 10-point PowerPoint presentation for a vector space, because if you can establish an existing vector space that we're working in, then we get to inherit all of the algebra properties that are so tedious to prove from the parent space. In this particular case, although we're working with 2 by 2 symmetric matrices, the general vector space we're working in is M2R. This is the set of 2 by 2 matrices with real entries, which is very similar to what we're talking about. And if you wanted to write that out, this would be the set of A, B, C, D, such that A, B, C, and D are real numbers. And to the untrained eye, it looks very similar to what I wrote up above, right? A 2 by 2 matrix and all the entries are real. This is a 2 by 2 matrix. All the entries are real. But when I write it this way, because I wrote both of these positions as being B, I am subtly stating that these two have to be equal to one another. That's the requirement. And if you go back up here, that's really the difference between what I'm writing down here for the parent space and what I'm writing up here. It's got this extra added restriction that these two positions have to be equal. So the devil's in the details, and make sure you're paying attention to that kind of thing. Now, since we have the quote-unquote parent space, our subspace S inherits the algebra of the parent space V. So I don't have to show things like distribution. I don't have to show things like commutivity. I'm already working with matrices that commute when I add. I'm already working with matrices where scalar multiplication works. The only thing I'm worried about is closure. Does adding symmetric matrices together beget more symmetric matrices, or does it leave the subspace? And so coming back up here to our little diagram, if I take a vector in this red line, say something like this vector here, this blue vector, and then I add it to another, oops, whoa, easy, Tiger. I add it to another vector that's in that same subspace. The sum of those two is a third vector that's also in that subspace. I don't get something outside of that subspace, so to speak, in terms of direction of a line or points on that line. That is to say, points on that line plus other points on that line beget points on that line. And so we're looking for something similar to happen here, and here's where it gets abstract. So we have our parent space. The next thing would be to make sure that I have a non-empty set to show S is non-empty. This is merely a matter of you showing me that there's at least one symmetric matrix in this space. You could produce any element of S that satisfies the requirements or restriction like this. Note A matrix equal to 1, 2, 2, 3 is a 2 by 2 matrix with real entries where the A12 and A21 position are equal. That is, it's not just a 2 by 2 matrix, it's a 2 by 2 matrix that has this symmetric property. So A is a member of our set S, and S is non-empty. So I'm not breaking the cardinal rule of trying to show you that the empty set is the space that we're working with, whatever that means to you. Now, there are other candidates, and this is an important one, second option, alternately. You might note that A equal to 0, 0, 0, 0 is an element of S, as those two positions are equal. Now that's often the easiest one to show, because if you're going to be a vector space at all, you have to contain the zero vector. And if the zero vector doesn't adhere to your restriction for the set, then you can stop your entire proof. Because if it doesn't contain the zero vector, then what we're trying to show as a vector space can't be a vector space. Note, it is often beneficial to try and show the quote-unquote zero vector, whatever that format is. Here it's a 2 by 2 matrix, is a member of S, because if it is, then S is non-empty. If it isn't, S may still be non-empty. Well, come on. But won't contain the zero vector, which means S cannot be a vector space. And as I said, in the very first part of this lecture, I'll come right back to this. Sorry, hold on one second. The very first thing that I drew for you, the very first talking point was, when we're talking about this homogeneous equation, we're guaranteed that zero is a member of the set. So as we go into abstraction from lines and planes to weirder spaces like matrices, like we're looking at our example now, one of the basic requirements is the thing that's called zero is in our set, and that should be an easy thing to show or come up with to prove that your set is non-empty, which is what I'm giving you alternatively here. Look, this thing that's called the quote-unquote zero vector for this particular set. The data structure that has zeros in all of its positions adheres to the restriction. And so it's an easy show or tell to show something is non-empty, which is what we're doing here. Okay, now to the actual meat of the proof, there's two more things that we have to show. 3, closure under vector addition. All right. So now that I've shown you that the set is non-empty, we can do things like let X vector and Y vector be in our set. Now this very next step is a Captain Obvious maneuver, and soon you'll graduate from second lieutenant to first lieutenant to Captain Obvious. But in a proof, you really have to lay it out for the reader. So when I say I need to do vector addition, I want to show you that when I take two symmetric matrices and add them together, I get something else of that form. The first thing I have to have is actually two vectors from the set to add together. And since we just showed that the set is non-empty, I can now reach into the set and produce a couple of vectors. And as a consequence, X vector is going to be some kind of A, B, B, C. So again, I have this symmetric 2 by 2 structure. And Y vector, whatever it is, I'm not going to make it the same one, but let's go with D, E, E, F, is another, oh, come on, another 2 by 2 that has that same symmetric structure. Now, consider X plus Y. You got to be real careful not to jump the gun here and go straight to the end. You're trying to do a proof and you have to justify each one of these steps. And the more steps you put in here, the easier it is to read your proof. This first step is just substitution. I am simply writing out the forms of the two vectors I just referred to or declared. And so this was, come on, dude. This was substitution. Man, my handwriting is terrible on this tablet, dude. Substitution. Then, in the next step, I'm going to use matrix addition. I would add those component-wise. I would add A to D. I would add B to E. I would add B to E, and then C to F. And so that particular step was how matrix addition, or in this particular case, quote-unquote vector addition, is defined. It's still a 2 by 2. The result here, A and D are real numbers, so that's some kind of M, N, N, P. I'm not going to use O here. But what I have here is, and we can see, symmetry. And then symmetry. And if I reduce it and call them slightly different numbers, I have symmetry. And this result is a member of S, 2 by 2, symmetric. And so the format is preserved. And so what this says is if I reach into my collection of 2 by 2 symmetric matrices and add them together, I have just proven to you that the result is always going to be another 2 by 2 symmetric matrix. So once I'm in the subspace, I can't leave the subspace or get something outside of the subspace by simply adding two elements together. So S is closed under addition as X vector plus Y vector is an S whenever X and Y are in S. All right, last step. 4. This is closed under scalar multiplication. let's see. In order to be closed under scalar multiplication, we want to show if x is an element of S and k is any real scalar, then any scalar multiple of the x vector is also in the set S. So we're going to let x be an S. Immediately, that's going to tell us that we're starting off with something that has this 2 by 2 symmetric structure. Then k times x is k times a, b, b, c, which again has that symmetric structure. And then I'm going to use the definition of scalar multiplication. This is Ka, Kb, Kb, Kc. I still have that symmetric structure. That is to say, those two positions are still equal. If you want to call them something different, you can, like HK. Oh, I already used K. I'm running out of alphabet. R, S, S, and T. This is another symmetric matrix, and it has the same format. So S is closed under scalar multiplication, the operation of scalar multiplication. So to recap then, and this would be good to do for your proofs, S is a non-empty closed subset of an existing vector space V. So S is a subspace of capital V. Please note the subtle difference here in the terminology I'm using, right? I started off with a non-empty closed subset, and then I jumped it up in status to subspace because of the closure and the inheritance of its parent space. And then the final statement in this proof, because it's a subspace, so S is a vector space in its own right. Ta-da. All right, we have about 7 minutes left. I'm going to try to get through one more example. Before we do, not that I was expecting any interaction, but anybody got any questions? You can throw it in the chat. You can turn on your mic. You can interact with me. You can ask me a question. Super fun. Oh, there's somebody in the chat. Where you at? Where's it? Oh, I can't find it. In the second matrix, what happened to D? I understand that B and C are equal. Shouldn't the matrix be A, B, B, D? Oh, yeah, that was just a matter of me changing the letter. If you want me to write it as A, B, B, D, you can. I just changed B to D to C, not because it meant where are we at here? Way back in the beginning. I already passed it. Where's the symmetric definition? Right here, right? This is what you're talking about. I had A, B, C, D, and then I said these were equal, and then I changed D to C. I'm just renaming them and reusing the alphabet. Don't worry too much about the letter I'm using, only the position. I'm saying here I can say there are 4 different letters, but B and C positions are equal, or I can just use the first 3 letters of the alphabet and say that that position is the same letter. So if you want, Ashna, you could just, I could do this. I could make that a D and make that a D. Is that better? Is that what you're talking about? Yeah, cool. So I'll just leave it like that. Be a bit more straightforward. But then I use A, B, and C, D here. Right? Do I use A, B, C? Yeah, so down here, I'm not bothering to call it. I don't even know what that position is. It's just a generic placeholder. And I'm just running through the alphabet one letter at a time. And I thought it would be weird to go A, B, D, or whatever. It's up to you. It doesn't even matter. You could use, get weird, you know? There you go. Arbitrary symbols at that point. Whoops. I don't know if you can see that. Yeah? Yeah. So they're just arbitrary placeholders. Okay. Let's see. Example 2. Let S equal the set of 2 by 1 matrices XY such that x squared plus y squared equals -1. This is an empty set. So that's going to be the issue here. So you could start off with the parent space. Capital V, the parent space, would just be R2. The set of all x, y, basically ordered pairs or 2 by 1 vectors, where x and y are real numbers, is the parent space. No big deal. And you could go about trying to show things are closed if you wanted to, but 2, S is empty. Or let's do this. Let's not even worry about it being empty. Show S is non-empty or contains the 0 vector. And so we might say, note 0, 0 is not an element of S, since 0 squared plus 0 squared equals 0, which is not equal to -1. So this vector does not satisfy the requirement to be in S. Now, that doesn't actually mean that the set's not empty, although this one is. So S cannot be a vector space. It simply doesn't contain the 0 vector. In fact, it's also empty. We would say here, note, S is actually empty unless we consider complex numbers, which we're not doing in this particular example. I'm about out of time. We're going to do a bunch more examples tomorrow in class. I'll see you guys then. Stick around if you got any questions. Oh, where's another one? Another question. When proving closure under addition or multiplication, would you want us to use variables, or could we provide a specific example? Okay, that's a great question, Andrew. Note, to prove closure is true, if you just come up with 2 specific examples, like with actual numbers in there, and it works out, you've only actually proved that it works for those 2 specific examples. So to prove closure is true, you must use general vectors. So to your statement, Andrew, you got to use variables. Use variables so that you can prove it's true for all cases. However, to prove closure is false, you only need show a specific counterexample. Use specific numbers, and we'll talk more about that tomorrow. Good point, dude. Can you go back to the final part of the proof, please? This part, Jackson? Or the other example? Yerp, yerp. All right, yerp. Super good. All right, folks, I'll see you tomorrow. If you're still taking down notes, let me know. I'm going to post this PDF too, dude. So you're going to have this on Canvas in just a little bit, together with the video. So don't sweat it if you missed any of this. I'm going to post it almost by the end of the day. It'll be up. Right on, thumbs up. And then, blow. Cool. You guys got any more questions? Jackson, Graham, you guys doing all right? You just hanging out? Later. Yeah. Well, let me stop the recording.